Let's wait for the clock. Okay, so 1 minute for you to challenge.
Question 5, the ping-pong rocket. Okay.
Ping-pong rocket. Reporter, and think about. 1分钟，你要 reset 让它冲一下。选择这上面吗 ？So you accept? Yes. You accept it. Okay. So, problem number 5, ping pong rocket. So all the presenters, please come to the blackboard and write down your name. So reporter, you have 5 minutes to prepare. Please get ready in 5 minutes. get ready.
Honorable judges and worthy opponents, this is reporter reporting problem 5 ping pong rocket. So for the problem statement, a ping pong ball is placed in a container of water, and when the container drops to the ground, the ping pong ball will get launched to a great height. So we'll be focusing on investigating the relevant parameters and maximizing the height. And as we all know that as the ping pong ball launches through, actually it will be affected by air resistance, which is hard to analyze. Therefore, we'll be focusing on investigating the initial velocity of the ping pong ball launching. So for the phenomenon, so when a container drops to the ground, there's an instant pressure what acts on the water container and cause this water to compress. So the instant pressure caused by this water compress based on the compression ratio that varies through temperature and pressure. And in this case, temperature and pressure will all be considered in later experiment. And also, the compression creates an acoustic wave that generates a vibration in the circular surface, circular membrane at the top of the water surface. So therefore, the energy generated by this wave will transfer to the ping pong ball and launch the ball up. So for theory introduction, we'll analyze how the ball is in equilibrium state during when it's not falling to the ground. So as you can see, this is the introduction. So here's the equilibrium between the buoyancy, surface tension, and the gravitational force. That the first term is the buoyancy, the second term will be surface tension, and the third one is the gravitational force. So through the notation we just mentioned in our introduction, we can substitute the formula to the formula above. So through anti-differentiating the force, we can get the work done by the buoyancy during the launching process. However, this is not the main effects of this phenomenon, that this velocity should be in minus value, since it actually starts, the ball didn't sink into the water. Instead, here is just trying to calculate the energy that when the ball is launching in order to access the water surface, what energy loss would be done due to the gravity force and the buoyancy force. So we'll get into our theory that we first calculate the force that's that's used to compress the water, and here's the equation 4. Then we can get the pressure, and based on the control parameter temperature and pressure, we can get the compression ratio and calculate how much volume is actually compressed in that process. So then we can find the acoustic pressure by applying the bulk modulus equation. And through substituting, we can get to equation 8. So in order to prove that when the container collides with the ground, this speed of the wave is really fast, that it reaches to the ping pong ball in a really short duration. We calculate the wave using the wave equation. So the coefficient of the equation will be square of the propagational speed. And as you know that the bulk modulus of the water is very big, therefore this propagation speed will be really quick. So, and the acoustic wave energy of the fluid will be like in equation 13. And for the second term, because the ping pong ball actually launches through before the container actually bounces back to the Therefore, the second term will be 0. And then we can calculate by using the pressure we just derived and get to our velocity, which should be, there's some part of the energy should be decreased due to the buoyancy and gravitational force before it leaves the surface. And for the experimental setup, by hanging the ping pong ball to a stick, we can make sure that the ping pong ball is at the center of the container. That is easier for calculation, and use the high-speed camera to capture the video that the ball got launched, and use tracker to analyze the initial velocity. So here are the relevant parameters. First, it will be the height of the dropping bucket and the existence of surfactant, and also the amount of water in the container and the surface area, different shape and different temperature. So first, as the velocity increases, the pressure imposed on the water will increase, and therefore the compression ratio of the water will increase. Yeah, as more water is compressed, this energy provided by this acoustic wave will increase. Therefore, it will provide an increase of initial velocity. So we know that existence of surfactant can actually affect the coefficient of surface tension. While it's mentioned in the first part of our theory, the equilibrium position of the buoyancy force, surface tension, and gravitational force. But we all know that this isn't the main effects of, it's not the main effects that will affect the initial velocity. Therefore, as you can see in this graph, it's still a velocity and height graph that with and without surfactant, the initial velocity will not change much. So for the experiment 3, the larger of the volume will cause the increase of acoustic wave energy. As you can see in this equation, the first term is included the integration of volume. Therefore, this integration of volume, this increase of volume of water will increase the energy that it can provide it to the ping pong ball. So it also presents in our results that it's an increase of initial velocity. So for the next experiment, we'll focus on the surface area. So as we all know in our theory that as the container collides with the ground, the force spreads throughout this area. So if the area actually decreases, it will cause each stress of the point the stress to increase. So the stress, as the stress increases, we have the higher compression ratio, and this higher compression ratio will generate a higher energy provided by the acoustic waves. And for the experiment 5, we analyze the different shapes of the container could have the effect on the results, since this different shape might change how the water surface actually vibrates. And however, as you can see in our experimental results, this different shape analysis doesn't really affect our results, and which we consider this is not the main factor that can affect the initial velocity or the launching height of the ping pong ball. And for the last experiment, we're focusing on analyzing the different temperature of the water that's contained in the container. So as we all know that the compression ratio of the water is actually affected by both pressure and temperature. So as the temperature rises, there will be more water being compressed due to the higher molecular average velocity in the molecular dimension. Therefore, since there's more water volume being compressed, the more energy will be generated and cause cause the ping pong ball to launch in the greater initial velocity. But as you can see in this graph, the temperature seems not to be the main factor, and it's only differently a little bit that although we switch the temperature of water from 20 to 50, it only increase a little portion in terms of initial velocity. So the problem statement states us to optimize the water. It's a bit vague since if you put the container higher as possible, it's reasonable that the ping pong ball will launch in the higher initial speed. So we focus on this optimization on the shape of the container. The problem statement states that there's only 2 liters of water. Therefore, in a conformed volume, we can change the surface area and the height of the container. So as we just find that this area is actually a main factor that can affect this initial velocity. Therefore, theoretically, the maximum initial velocity we can reach will be upon the stream. So next, I would like to analyze some possible deviation that may happen during the process. That the friction between the water and the container can actually causes an energy loss. And also, during the compression process, the compression can raise the temperature of the liquid, which means the compression ratio can be changed throughout the compression session. However, these factors will not be the main factors that affecting the whole phenomenon, because this compression time is actually very, very fast. Therefore, it will be not such a significant change. So for the conclusion, this is our velocity, and if we ignore the air resistance, we can get to our height. But air resistance is still a relevant parameters that it's hard to analyze. And thank you.
Okay, thank you.
Okay, so another formula. And first, I want to know how do you define the height of the ping pong ball? Because when you drop the ping pong ball, there will be 2 directions. And first it's vertical, and next it will jump to different directions. And how do you measure it? If it drops like this, and you will measure this, or just straight to the ping pong ball.
So I think you're focusing on the velocity, that if the velocity will deviate from the vertical direction, it means that the container actually drops to the ground with a certain angle. And this is not part of our experiment because we exclude those times that when the container drops down to a certain angle and cause the container to tilt.
So you only think about the initial velocity.
Initial velocity of the
ping pong ball.
Yes.
Okay,
correct.
next, and in page 3. Okay, it's okay. And I want to know, do you think the temperature really affects the result very much?
As you can see, we have done an experiment focusing on the temperature's effects on compression ratio, and this result is not that significant.
Okay, so wait, and do you think that temperature is affect the surface tangent, so the surface tangent affect the result?
I do acknowledge that the change of temperature can cause different effects on the surface tension, but we've also done an experiment of the surface tension and proves that this surface tension is not the main factor and its effects can actually be negligible. Therefore, this increase of temperatures can affect this phenomenon by the increase of compression rate ratio.
Thank you. And what's your answer of your experiment, the maximum height?
Because it's hard to analyze when the ping pong ball launches through this. It is affected by air resistance, so we're mainly focusing on the initial velocity, which is definitely proportional to the height, launching height.
And
Sorry, time's up. Okay, so the opponent, you have 3 days to prepare. This is coming. 下，他们还没投出来。
I want to explain my presentation. Okay, so this is a task. I think you already know it, so just keep it. Okay, first, your solid part of your structure is first the phenomenon, and you have a theory to prove it, and use the experiment to prove the theory. That is the theory. You use the modulus equation. And first, I think you have a relevant modeling to the theory and a graph to explain the theory. But I think you didn't clear how modification of theory was actually done and the lack of the explanation of your theory. And this is your report. I think it is simple, understandable explanation of the phenomenon and the appropriate use of media. But I think lacking explanation of the accurate connection between the theory and experiment, I think you can improve this. And the graph, data graph, I think it is hard to understand. It's just like a little bit messy topic. Yes. So I have some points I want to discussion. And the first is the air resistance, and next is the diameter of the cup. And third, the experiment device, and last one is the Washington jet. Okay. First, I want to know the surface area. How do you define the surface area? Is the water surface or just the bottom of the container?
It's basically uniform. The surface area of the bottom of the container is quite similar to the surface area of the container above the surface of the water.
Okay, so and you know and you do the experiment of your heating area of your container, right?
Yes.
So do you think you actually have the same heating area in your experiment?
What do you mean by the same heating area?
Because you do the experiment to prove your theory, and your theory has a heating area like the P equal to the area, right? The ratio.
Pressure.
Yes. And I want just because your experiment also do it, and when you drop the container, it will tell to you to make sure it won't rotate when it's falling.
What rotate? Just the container?
Yes, your experiment.
It just won't rotate. What do you mean by rotating container?
Just and because I think your hand is not able to do this.
Oh, you mean that the stream might cause the container to rotate a bit,
Yes, yes.
and you're thinking, actually you can stabilize the container before falling down, and this can largely decrease the possibility of the container rotating throughout the process.
Okay, and Sherman, can I use the backboard? Okay. Also, at first I want to know if your container drop is on the floor just like this. And first, when your heating area is like this, the jet will be landing right. But when the heating area like this, the pressure will drop like this. So it will not like this. It will. The pressure will be like this. And if your container is this. So I think when you drop like this, your container your water will hit your container, and the energy won't transfer totally to your bowl.
I mean, because you're imagining that when the container actually collides with the ground, it's tilted. But as I just mentioned during the last discussion period, we exclude all of the times when the container actually collides the ground with an angle. However, we only use the times when the container actually perfectly collides in a straight way to the ground.
So just like you said, the initial velocity.
We analyze the initial velocity.
Okay. And next is in page 4. The contact angle. I want to, and because the ping pong ball is a red substance, so I think that contact angle won't act like this. It will just left up by the surface tangent. Yep.
Can you rephrase?
The ping pong ball's contact angle will like this. This is the contact angle.
Okay.
So your contact angle is weird. And next I want to, and your experiment setup. And how do you know this ping pong ball will in the central of the surface?
That's part of our experiment setting. That if we analyze it through the high-speed camera. So if we found out that the ping pong ball actually deviates from the center, we will not use that data. We only choose those that's actually in the center of the water.
So I think you can improve your experiment in another way. And next I want to know, do you know the Washington jet?
Yes. So we're considering. We're considering a Washington jet. I assume that it actually states that when the ping pong ball drops to the ground, it creates a path.
Yes, a path
like this.
Yes.
Therefore, the velocity force will punch the jet, and in order to punch the ping pong ball up.
Yes.
Can you show the video? So, just wait a second, please. Sorry, I'm waiting for this video to get to the point. So, you can see that in this video, the ping pong ball actually doesn't sink into the water in order to create a path. So, because it didn't create that kind of path, there won't be such an impulse that pushes the jets, like the Washington jet you just mentioned. So we believe that Washington jets actually doesn't fit in this problem.
About the Washington similar to the Washington jet, and we know there's a contact angle also in the cup, right?
Yes.
And your ping pong ball is just like this. So this is the pressure. Yes. The pressure. And we know when you jump on the floor, it's also a pressure. And when it's falling, it's on the air, it is wetted, right?
It's what?
Wetted.
Yes.
Yes. So if like the contact angle, when it's falling on the ground and in the air, the contact angle first, when it's on the floor, the contact angle acts by the surface tension pushing up and the gravity pushing down, right? But in the air, it won't have the gravity.
Yes.
So next, the contact angle will change and walk over. So I think next I want to expand the diameter of your cup and you consider that it will affect.
So the diameter of the cup is actually correlated to the area of the cup. It's considered in our theory.
But you consider this.
I think you consider this because you use the theory of Washington jet in order to create a path. We're not using that theory, so we believe that that's the minor factor in our problem explanation.
Okay, and so in the end of our the initial velocity, you say the initial velocity is proportional to the maximum height.
Yes.
And do you consider in the air resistance? Because
I think it's positive correlated rather than proportional. Proportional is not a good word. I'm sorry about that.
so you know the initial velocity, right?
Yes.
So you can know the air resistance for the formula. And then if you combine this, you can know the maximum height.
So the reason why we didn't analyze the height rather than but analyze the initial velocity is that as you know that this air resistance, if we're trying to reach the maximum height, we will like the ping pong ball to remain in a straight line in a y-axis vertically all the time. But it's really easy for this air resistance to actually tilt the ping pong ball. And so we analyze the initial velocity due to that, because the height is really hard to measure.
I think you can still consider it in your theory or just in the theory but not in the reality. Because we can't even do the same experiment of our theory, right? Because it's just like some mistake in our experiment.
Because I personally believe that if we can't actually verify our theory is not, by experiment, it's not really necessary to include it in our theory, since the point of the report is to prove our theory through the experiment. And since we can measure the height, that it's really easy to tilt, I focus my report on measuring the initial velocity.
So you still think you can still know the initial height, initial velocity, you know the maximum height?
Are saying that we can use the initial velocity to derive a theoretical maximum height. That's correct.
But you didn't do that.
Because it's not really, it's not be able to measure by experiment. So I don't think that's important, because the point of the report is to validate my theory through experiment. Yes.
So the conclusion of your initial velocity is your theory result or your theory result or your experiment result.
Which one?
Your initial velocity in your conclusion.
You meant the optimization.
Just I think turn to page the last.
This one?
Yes. So this is the theoretical velocity.
As I just said, that because if we're maximizing the height, it's reasonable that if we place a container higher as possible, the ping pong ball will launches with a higher initial velocity and reaches a higher height. However, this is not really useful of analyzing this physics problem. Therefore, I focus this optimization on the shape of the container, and that's the point of this page.
So, I think you just you can know the theoretical velocity, but based on some reasons, because just like the air resistance, it is not hard to calculate, so you can't know the maximum height.
it's not hard to calculate. By solving the differential equation, you can still get the theoretical results of this maximum height. But I think it's not really important to this problem, since you can really validate your theoretical value through experiment, and I think that's the point of the report.
What's the maximum height is the problem asking?
Because in order to reach the maximum height, you're trying to reach the maximum initial velocity. Is definitely related. That's what I thought of this problem.
Also, you just simulate the problem is not similar and it's not the same to the problem.
Sorry?
Simulation. You do the simulation.
Simulation? No, I didn't do computer simulation.
No, me, because the question is asking for the maximum height, but because you want to do the initial velocity, that because initial velocity is have some positive relation to the maximum height.
So here's how I see the question. I believe that if you want to reach in maximum height, you have to reach in maximum initial velocity. So that's why I analyze in the maximum initial velocity.
Hands up. So the opponent, please summarize the discussion in 1 minute.
Okay. So first, I asked about the heating area, but I think it's not from my theoretical explanation. And next, the maximum height you didn't calculate it, but I think you still have some method to calculate. And third, the both contact angle and the Washington jet. And you said you think it is not thanks to the theory you use. So I think, okay, I believe to you. And then the container, I think we can use a better container, just like a square. It's not like I think it is quite weird. And okay, so the surface, your water and your bowl is not in the central. I think there's some method to improve your experiments. Okay, that's all. Thank you.
Thank you. The reviewer has 3 minutes to ask questions.
And the first question I want to ask for reporter is what role does the water jet, the Washington jet play in this phenomenon? So it will consume the energy, will give the ball the energy.
You're asking. As I just mentioned, as you can see in the video, that the ball didn't actually sink into the water in order to create a path of launching the Washington jet. Therefore, we don't fit Washington jet's theory in our product statement.
So you think that the water jet is not important in this phenomenon?
No, Washington jet doesn't mean equals to water jet.
I mean water jet.
I mean water jet. So we believe that the water jet created in this phenomenon is through the acoustic wave.
Okay, thank you. So Apollo, what do you think?
And
So water,
there is a pressure in the surface, so I think that the Washington jet has some relation to the jet and the both height.
I think the Washington jet is consume the energy or give the ball the energy.
It will concentrate the energy from the bottom of the container.
Okay, thank you. And the next question I want to ask reporter. Did you consider air resistance in your model?
As we just discussed, our
Yes or
report
no?
mainly, sorry,
Yes or no?
we focus on velocity.
Okay. And do you consider the rope tension in your model?
Rotation
Because
of what?
rope tension. Because you use the rope to let the container drop vertically.
There's no such a rotation because the way we actually let go of the container is we let go of the rope. Therefore, there is no such a point that the rope is tied up to something, and there will be not such
Okay, thank you.
rope tension.
And the next question I want to ask reporter. In your model, you didn't consider the air resistance, right? In the velocity
That's not the
model.
main focus in our report because
So I want to ask why your data is so stick to the theoretical line. Why?
because we didn't focus on the air resistance. We didn't analyze the height. Instead, we analyzed the initial velocity.
But the air resistance might affect the initial velocity, right?
No,
Why?
because it just won't affect. Because you're not launching the ball through the.
Okay, thank you. And can you tell me the definition of the initial velocity?
The definition of initial velocity is when the ball leaves the surface.
Of the water?
Yes.
Okay. And did you consider the energy loss in the model and overall duration?
Sorry, time's up. So reviewer, you have 2 minutes to prepare. Reviewer, please take the floor.
Hello everyone, my name is Amber Echo Awan, and today I'm going to review problem number 5 in homework. Initially, our problem statement and we will mainly focus on the maximum height that the ping pong ball can reach in every experiment, especially the reason that makes the ping pong ball reach at different maximum height. And for overview the report, we have the model of the initial velocity, and then I think picture is the demonstrate the full model, and then consider the contact angle between the ball and the container, and her cone is he didn't consider air resistance, and if he used the rope, it didn't consider the rotation. And for the external data and parameter, he had the shape of the container, and he had the shape of the container and the water value of the water value and the release height of the container. And I think his proof is he had allowed experiment of conducting, and he calls it in. He didn't measure the maximum height, which is mentioned in the problem statement. And in data analysis, he just analyzed the initial velocity, and he didn't analyze the maximum height. I think this is very important for us to measure the maximum height because the problem statement says that we need to measure the maximum height. And for the review of the opponent, we have mentioned about the initial question. He had mentioned the contact area of this and why he didn't measure the maximum height. I think he asked a critical question about it and point out that the reporter didn't have the maximum height in a report. And for the discuss part, we have for the discuss part, he had mentioned the reputation between the. Okay, I just get to the key discussion. Well, the opponent asked why didn't consider air resistance in your model, and the reporter said that the initial velocity will not be affected by the air resistance. I think that the reporter said that they cannot get the exact number of the maximum height because of the air resistance. I think it is theoretical-like problem in the discussion part. It will affect the result that we think we need to consider in the theory. And then our question is, what role the water jet plays in this phenomena? It will consume the energy, will give the ball energy. I think both of the water plays both of this role. And the reporter say that the water jet is not important, and the opponent say that the water jet consumes the energy. Thank you.
Thank you. So, reporter, you have 2 minutes to conclude.
So, honorable judges and party opponents, here's the concluding remarks. Both the opponent and reporter focusing on the fact that we didn't measure the maximum height, which is stated in the problem statement. However, we believe that the whole problem's focus is actually analyzing the process of the ping pong ball launching through this upward. Therefore, we provide quantitative analysis of initial velocity and a qualitative analysis for the height. So I don't think I think that's another way of fitting the problem statement, since we can understand this increase of height through the increase of initial velocity. And also, the reviewer mentioned the rope tension that should be considered. I don't think there's such a rope tension that when in our experiment setup. However, there's a friction between the rope and the hanging point, and I think that's the point that what we're trying to state. But we all know that 2 liters of water in containers has really large mass. Therefore, this gravity force can make this friction be negligible. And the opponent mentioned that since we didn't find a valid way to stable the ball to the center of this container, our experiment should be improved. But we stated that we did exclude the experiment samples that when the ball isn't in the center of the circular membrane. Therefore, I believe that the lack of stabilization of the ball didn't really affect our experimental results since we exclude those deviated samples. And we thanks for the suggestions from opponents and reviewer. Thank you.
Okay, thank you. So now, we welcome the question from the jury. So, any question from the jury?
Just for 301. First for on your report, I saw a value since you mentioned in those initial velocity is roughly 100 meters per second, right? I would like to ask you, do you think is it reasonable or not?
Sorry. So the optimization of velocity of 128 seems absurd. However, that's because we actually minimize the area of this container. Therefore, it will be the shape of the container is actually not be able to obtain through in the real life, since there is no such a shape that can contain 2 liters of water where its surface area only suitable for 1 ping pong ball. So that is actually a theoretical value that we would like to fit in to answer the question. If you want to optimize the height, you would like to provide such a container. That's what I'm trying to say there.
And so the initial height, I think, is the height where, and because I found a question about it, but because the container will tilt because your surface area, right? The surface area will change, right? In your experiment.
Can I answer?
No, I just asked you, do you think the value is reasonable or not?
I think that is weird as well.
Pardon?
I think that is not.
Why?
You mean the initial answer?
The initial.
Okay.
You mean the area that the reporter has?
Yeah, the maximum initial speed they expect.
I think it didn't make sense because when the water jets like this and will push the ping pong ball out, I think the ping pong ball may have some rotate and also need to consider the air resistance.
So following this question, I want to ask all 3 of you that because question is asking us that how to max the maximum height, also correlated to the maximum initial speed. So what's the key parameter you think? Just let me know what's the key parameter.
I think it's the surface area.
I think it's the initial height.
Initial height.
I think it's the initial height.
Okay. Other?
Does surface tension play any role in your theory?
In my theory, I consider surface tension as a negligible factor.
That's very strange to me. Are you aware of the experience of the French group that if the ball is in hydrostatic equilibrium and you impact it with great force from bottom, it won't jump at all. The reason that the water jet works has to do with when in free-falling state, gravity is of no importance, only surface tension and resistive force are operating. And it is surface tension force which pulls the ping pong ball into the water so that it displays more water, that is more mass, than it does when it is in hydrostatic equilibrium. And that makes the momentum transfer very large compared to the hydrostatic case, so that the water jet forms. I think this is well known. So in your theory, I fail to see that you use the conservation of energy, right?
Professor Tsai, sorry, so we should make the question shorter. Probably later on you can give a comment.
So what's the
Because
question?
there's really no time.
Sorry. So you still have any question wanting to answer?
My question, they cannot answer my question, actually.
Yeah.
Because I studied this water jet problems, and it even use it as a theory 1 of A4 competition. This is actually kind of a water jet problem. When you stop water quickly, pressure builds up, the pressure wave rises. Now, in slender pipe, it's plane wave. It's it just wavefront is plane. But in this case, you have a larger dimension when the water from the wall, the sideways, they will converge and try to push up forming an actual jet which push the ping pong ball up. So this is actually a very interesting problem, but you use energy principle, you don't understand the dynamics at all. So that's a pity to me.
Yeah. Okay, so I think it's time to give the score. So please prepare your score. Okay, so first the score to the reporter. 5, 6, 5, 5, 4. Okay. Secondly, the score for the opponent. 5, 7, 5, 6, 4. And lastly, the score for the reviewer. 5, 6, 5, 4, 4. Okay, so I think the jury give quite consistent to all three of you, so probably you skip the comment. Yeah. Anyone want to give comment?
My comment is
Yeah.
study the papers by the French group and Japanese also listed in the international. Also, you should watch IPO. No, that's called International Fitness Tournament. 2020, Russia is the champion. They did this problem. Watch it. And compare it with your insert very detailed presentation by the Russian group. Very impressive. Moscow Institute of Technology, Science and Technology, MIPT. Physics and Technology.
Okay. Okay, thanks for the suggestion and comment on the jury. So let's stop here, take a short break. Please change the table.